Welcome to the Probability Podcast. Discussions on emerging and converging technologies, problems that are being solved, and the probability of positive and negative outcomes that we might expect. Now, please welcome your hosts, Jason, the generator Spracklin, and Patrick, the discriminator Lozon.
Hi everyone. The topic for this episode is quantum computing, an innovative field of computer science that harnesses the principles of quantum mechanics to perform complex calculations and solve problems that are impossible for traditional computers. So, the questions we are posing today: what is quantum computing and how is it different from classical computing? What are the most impactful features of quantum computing? How will quantum computing disrupt and advance various industries? As well, how will this technology supercharge the evolution of AI? And finally, what are the current challenges and future outlook for this groundbreaking tech? What do you think, Patrick? Are we ready to take a quantum leap into the future?
I think we're leaping. Whether or not we want to, land in a good spot, that's I guess that's up to the technology.
Do you remember that show?
Yes,
the Quantum Leap show. We always do some kind of throwback to something from years gone. Quantum Leap was a show where this guy would figure out how to leap into other people's bodies in different periods of time, and found himself in situations that he had to solve problems for them. And once I believe this is the case, once he solved the person's problem, then he would just leap to another body, and it was this the show was this perpetual cycle of him leaping from body to body and trying to figure out how to get back to his original body, I think.
Yeah, I don't think he ever made it. Poor guy.
I can't remember how it ended, actually, but there you go.
Yeah, I there's a new one on, too, if you didn't know that already.
Oh, did they remake it? Leap. Oh, okay.
Yeah. So they loved it so much. But anyway, let's talk about quantum. No, the other problem with this particular topic is it gets a little, hairy, scary. It can be a little technical. So we'll try to make it more fun, but we'll have to dig into some of this a little bit so everybody gets an appreciation for what's going on here. So, everybody knows the transistor. It was created somewhere back when, 47 or something like that, with the vacuum tube. And ever since 65, that's when they first coined Moore's law. It was that, these transistors were growing, evolving at an exponential rate, well, at least double anyway. So the intent here is, there's an expectation of ongoing growth in the same, in this quantum field as well. But, I think we've actually reached around 30 billion transistors per chip now, which is incredible, right? But now we're starting to see really strange behavior, right? When you start getting that small, then you're getting into the world of subatomics, right? The quantum world. And, things start flipping bits, right? We start seeing noise and strange behavior. So we're actually hitting this quantum wall, right? So the intent here, of course, is, okay, if you can't go much smaller, then where you go from here? And the idea is let's move into a new methodology, a new type of transistor, a new type of processing. And it's not just going to be, on off, right? It's going to be on off and just, maybe, right? On off and maybe. It could be off, it could be on, right? And with that, that's the equivalent of what we call, quantum state, right? The subatomic world is pretty different in behavior than the macro world, right? And if you look at atoms, when they have all these particles like electrons and protons and so on orbiting around an atom, if you want to know exactly where they are in that orbit, or if you want to know exactly what spin they have and orientation, that kind of thing, you don't know. You simply don't know. It's all about probability at any given moment. And if you actually try to measure that, if you find a method to measure it, then what they call that collapsing the probability state. and you measure it, and now it's that, right? Where before it was just this, cloud of possibilities. So think about a, heads and tails with a coin, right? That's pretty straightforward. That's our, standard, binary approach for all our
Zeros and ones.
Yeah, zeros and ones. But think about a spinning coin, right? It's heads and tails, right?
Mm.
At any given moment. And so that's what we're kind of dealing with in this, subatomic.
Well, how very fitting for the probability podcast. So, maybe we're the first quantum podcast because we're not zeros and ones, right?
That's right.
We're constantly spinning and coming up with probabilities of outcomes.
And dangling. We're also dangling. So the other thing too is when you think about when you start going in that world, you get this really strange behavior of the fact that you can be, modifying a certain electron, and another electron could be entangled with that other, with one another. And when these electrons that are entangled, they will actually act exactly the same. There'd be mirrors, right? So there can be light years between these two electrons, and they will act exactly the same. That's spooky at a distance. So the idea is if you're into the entangling side of things, and you utilize that in this, subatomic world, you can actually build groups of these particles, right? And then you can utilize them to scale up, and you can do these big mathematical functions, right? That are in the next, you get a next scale, the next scale, the next scale, and with that you can, get into a situation where you can do some very complicated, what they call, complicated numbers, but very very complex, large calculations on a huge populations, right? And then what you end up being able to do is essentially perform, functions on big data and come up with answers where, other, the standard fashion of calculation fails. It would take 30 years to calculate something, and, go through this same calculation with the, a quantum computer, and it takes seconds, right?
Yeah. So why was it that Einstein referred to as spooky action at a distance? Was it really because they couldn't explain it? Because they basically said information cannot travel faster than the speed of light. So how is this second particle guaranteed to be found in the corresponding state instantly when the measurement of the first one is performed? So it's kind of interesting that, have we even solved that now, right? We're still trying to unlock the mysteries of the universe, right?
That's right. Yeah, we have this mystery, but nobody understands why or how it works. It just does, right? And this is the subatomic world, and it's not like you can, unlike your favorite Marvel character, we can't shrink down, and see these little guys at work, right? It's just not observable, only indirectly observable, which is, that makes things even stranger, right? So with all that in place now, the idea is, okay, can we build these, computers built of, this quantum mechanical process, right? And well, those atoms, right, are, if they were modifiable, then, can we modify the spin? Can we modify the, the actual number of, like if you look at an atom with and you add specific electrons to it, change it from an ion to, a particle with multiple electrons and that kind of thing. So there are ways of doing that. And there's many ways of doing it, actually. So quantum computers utilize, I'll go through this in a little bit, but there's multiple types of quantum computers, and nobody's really figured out which one's the best yet, right?
Oh, interesting.
Yeah. And with that, of course, what do they call this stuff? What's the terminology? So the terminology they call that, they use for this representation of a bit, a quantum bit is a qubit, right?
A qubit.
Yes. Enter the qubit. Yes. And with that, of course, we should recognize the fact that all the ideas behind this is really by a number of different physicists. So, there's Paul Benoit, and there's Richard Feynman and David Deutsch, and there's a few other ones from through IBM Labs and that kind of thing. So it's really a lot of work that had been done to build out these ideas of how you could use, quantum behavior to actually build a quantum computer, right? But nobody could actually do it, at the time. But they could. It was more of a theoretical, game, a challenge, right? But now we can, right?
Mm.
And that's where things get really interesting. So now when we look at computers now, we say, okay, what's a quantum computer? We'll have to talk about the different types, but the reality is they're in their infancy, right? They're little babies, and we're still learning how we can make them work, right? Work well for another. And there's lots of new ideas coming down the pipe, and lots of different technologies that are being tried out. What can it do for us?
Yeah, so I guess there's many potential areas that where we can be solving problems with quantum computing. If we look at the way it's being used today, it's accelerating discovery and research in many sectors, including health, new materials. It's being used to basically tackle encryption, either I guess creating stronger encryption or defeating existing encryption. Right? The idea is that it can really crunch huge sets of numbers much faster than what we have today. So the advent of quantum computing is going to create a lot of opportunities, I guess, and challenges there. We'll probably touch on this a little bit later, but certainly the combination of quantum computing and AI is massive. It's just going to accelerate that growth, and we already, we think it's growing fast now. Just wait till, quantum computing becomes sort of mainstream. It can also solve large-scale logistical challenges, performing chemical or chemistry calculations used in modeling, that type of thing. There's a lot of different areas. It's we're probably underestimating where this can possibly go in the future, right?
Yeah, and the hype may be more than just hype. The hype may be underestimated in the end of this. That's the really interesting point.
Yeah, so maybe we should get a little bit into like what a qubit is. I mean, I think everybody's really familiar, with the idea of zeros and ones, in traditional computing, which is sort of on and off, right? And so,
Yeah.
what is actually, what do we mean by a qubit, and how does it compare? I think we probably should dive into that a little bit further.
Yeah. So I mean, the idea of these computers are utilizing some kind of circuit, right? A representation of a qubit is really a number of different particles within a medium, or within a field, or isolated down to a few number of particles, right? So even though a qubit, you can view it as one, but it's not really one. It's really a group, and they're trying to isolate. And I guess that's really the challenges when we get into saying that we have a particular, atom, and it's accompanying, orbiting electrons and protons and stuff, and we're able to, look at those particular electrons and, actually isolate what spin they have or something like that. The other side of it would be, well, we can add electrons or pull electrons away from a particular atom, so there's some definite methods here that are being used, and I got to tell you, I'm not a physicist right? So I wish I could explain a lot of this stuff, right? But I'm doing my best.
Yeah, at a
So the
basic
idea,
level, I was going to say at a basic level, it appears that we're trying to find ways to drive electrical current faster, right? That we're essentially trying to speed up the computing power, and then the traditional method of zeros and ones on and off, it reaches, like you said, it's kind of hit a wall in which there's only so fast we can go. There's only so small we can make these transistors to fit into a chip. Whereas this is a completely different way of doing it, in which you have this constant state of being, I guess, right? To where
yeah,
you can really have a supercharged flow of electricity through these quantum computers in a way that we never could before. And in fact, it talks a lot about, because of the intensity of the electrical current, it has to you have to cool it to near absolute zero, which is minus 273 degrees Celsius, which is about
yeah,
as
these are superconductors. In order to be a superconductor,
mhm.
right, you have to really, really bring down the temperature, right? So you use like helium or something like that, liquid helium, to cool things down to minus 273 or close to that. But you want to get quite cold, right? And then you have this absolute, you know, when you think about ohms, you think about electrical resistance and that kind of thing. They're trying to eliminate that completely, right? So that's where you utilize these superconducting systems that so you can have these super cooled superconductors, right, as a target, or you can have these trapped ions, right? And that's why I talked about the field, right? And so they're trapped in an electrical field, and you manipulate them. You shoot little tiny lasers at them, and you can modify these grouped ions together and make them behave certain ways. Um, but you can also have electrons that are basically they're on a silicon-based circuit, so you can modify them. There's also you can have atoms suspended by laser light, right? The photons are actually colliding and suspending these particular particles, and so you can then perform certain microwave or whatever functions against them, and then change their properties. Um, the other one is, which is really interesting, because this is actually a Canadian company that's working on this, where they're using photons, right, and photonic circuits, light circuits, right, and the intent, of course, is to come up with these different ways of building these quantifiable atoms, or in this case photons.
Yeah, everything has an evolution, right? It's
Yeah,
like for the longest time, all of our internet was traveling through essentially copper wires or
yeah,
different types of wires, and then along came optics, right, and the ability to transfer information via light, and then now we're dealing with fiber optic internet, which basically gives us, the kind of speeds that at one time only like a large business would have, for example, right? Now everybody has a 1 gigabit or more connection at home through fiber optics, and that's essentially transferring data through light on the inside of these wires. So I think it's sort of the same idea, right? That
yeah,
when we evolve the medium of what we're transferring this electricity through, we can sort of amplify it, and at the end of the day, push more information through and solve problems faster, essentially, right?
yeah, yeah. That's right. And there's a lot of work being done, just as an addendum, on these photonic CPUs, right? Where they're figuring out different logic gates and how they can function for electronic type of equipment. So in the end, it won't necessarily be electricity that is being manipulated. It might be light. So definitely some very cutting edge stuff that is occurring around this experimentation and in this industry. If you think about the fact that there's got to be a starting point from point of view of comparing all these different technologies. they utilize it by saying, well, how many qubits, are you actually, powering your system up with, right? So you look at IBM, they have a quantum eagle, it's 127 qubit, and they got something called the Heron, it's 133, and the Osprey, it's 433 qubits. And you think, oh, that's really, really powerful, 433 qubits, right? But keep in mind, I think I said, was it 20 billion on the transistor? Um, so we're a little bit away from that equivalence that we've achieved on the electrical side. A little bit. Right?
I feel like our audience is are like Doc Brown right now in Back to the Future when when Marty says we need to generate 1.21 gigawatts of electricity in order to power it, and the only way to get that is through a bolt of lightning. And Doc says, "What the hell is a gigawatt?"
Yeah. And I think that's what we're dealing with right today is um, people. I mean, we're to be able to picture, this system and how it's working and what it has potential to do. I mean, there's just too much out there. There's too many, complementing factors here. And if we think about, okay, we're just going to use this qubit number, right? And how many qubits you got, right? That defines the power of the system. Well, not necessarily so, because it depends on how, this quantum computer is built. And I've talked about the different types, right? And those technologies, some of the technologies are inherently slower, but they're more accurate. And other ones are faster, but they have a higher rate of error, right? They're less accurate. So, and this is what's exciting about this field is nobody really has really defined. Oh, here's the best way to do it, right? Here's the way we build this locomotive and go across the country. Nobody really knows yet, right? We're still working at this, and so it's the frontier, right? And which brings me up to a point here: the HP Frontier. Yeah. So the HP Frontier supercomputer is the world's fastest computer at 1.1 quintillion floating point operations per second. I don't know. I can't picture 1.1 quintillion. Can you? That's a lot of stuff, a lot of operations.
Quintillion. I think that's how Bill Gates measures his bank account.
Yeah. So this is they had a, I don't know if it was some form of test or calculation on a prime number or whatever. The Sycamore quantum computer was able to resolve an answer for this in a number of seconds. And they estimate that the same calculation using the standard HP supercomputer, our best of the best that we have today, would take 47 years, right? Now, whether or not that's 100%, the numbers are 100%, that doesn't really matter. What really matters is there's a magnitude of calculation speed capability here we're talking about. And once we have
huge delta, right? The difference between a few seconds and 47 years.
Yeah, exactly. Right. So when we talk about, okay, what's the most thing that's profound about quantum computers? Well, that's the first thing, this magnitude shift, right? This exponential processing power. And let's say we get that tomorrow. What can we do with that? Yeah. And of course, I'm sure, on the academia side, we have a whole bunch of intractable problems that we haven't solved, these equations that we haven't solved. But yeah, so now we come up with some answers for some, our math curators. But so what, right? Is that really going to help us? Well, yes and no. I mean, some of these may help us build, some very complicated systems, right? If we can figure out and learn how to manage large data sets, for instance, we can actually manage really, really big complex systems. What's the biggest complex system you can think of right now? Well, I would tell you, the first one that comes out of my head is weather.
True, yeah.
right? Because when you think about all, like they're talking about a planetary set of variables that are occurring, the little butterfly waving its wings, you know, to, a little bit more rain in the one part of the continent or whatever. So this, even the mild changes in perturbances and temperature and that kind of thing, currents, it's incredible when you think about weather. And if you build this, quantum computer, it could soak all this information up and come up with, you know, uh, very probable predictions, right?
Well, it's sort of it because it's based in these quantum mechanics and atoms and molecules. It ultimately we can probably unlock some more secrets in the universe, right? I mean,
Yeah,
I think
yeah,
that's kind of the idea is that our idea of computing right now is primarily based in technology that has existed for a long time, long before we had generalized understanding of the elements in the universe. So perhaps this will unlock. New philosophical understandings, and we're always trying to reach these things like cold fusion and generating electricity right through means that are cleaner and that type of thing, and so despite all of our advances, we're still trying to develop clean energy. If you look at most nuclear energy, and they have these they have this waste that's extremely toxic. We create electricity, but if you look at what happened a number of years ago when they had that huge earthquake in Japan, you had this sort of byproduct of the nuclear stations filtering into the ocean. That was certainly going to make for some interesting fish swimming around, I think, in that area. But that made it all the way to California in very small
yeah,
trace amounts, right? So, like,
yeah,
while we've moved away from things like coal generating plants and that type of thing, we haven't gotten away from the problem of creating this waste that ultimately has to go somewhere. So maybe we can unlock some secrets that'll help us progress in that area as well.
yeah. I think you hit the nail on the head when you think about it. What are the key problems of our society and our world today? And that is being able to produce, you know, clean energy, right?
Hmm.
Being and stop, affecting our environment in such a negative way, like the old oil and gas and coal and that kind of thing. So that's definitely, if you think about if you had the smartest computer, right, being able to solve, you know, all these incredible calculation problems, and then on top of that, you build these AI, engines, and which is kind of a software, construct, and then you start feeding it in these new problems.
Hmm.
These things can handle huge data sets, right, and all these different feeds, and isolate through raw computing power, um, possible answers, right? So what does that all mean? That means whoever gets this, that we're going after that golden fleece, right?
That's what I was named after. When I was born, I had beautiful blonde hair, and my father named me Jason after Jason and the Golden
Chase,
Fleece,
that's right.
which I believe is a.
There you go. That's perfect. Yeah, yeah. So I mean, the idea is, is it unattainable? I think we're at the very precipitous edge of being able to attain this. If we don't end up killing ourselves with a world war, we could.
Well, we're already hitting that problem, right? We're already
Yeah,
hitting that problem of AI needing massive computing resources. So they're building these, huge data centers. They're having to liquid cool them, right? And they're taking up huge amounts of electricity and water, just to get the computing power needed to
yeah,
drive these AI models. So if you think about if these quantum computers can produce high amounts of processing power without the same need. Although in some cases it sounds like right now they need to be cooled by liquid hydrogen to get to a certain point, right? So maybe the same problem exists, theoretically, but if they're much more powerful, then maybe they need less resources in order to operate, an AI system that right now
yeah,
needs a massive amount of what you would call classical like computing power, right?
yeah. You have to use a lot less energy to come up with to perform the same amount of, or a magnitude higher amount of capability, right? So that's a big, that's a neat game changer there. The other thing, of course, is we think about these computers as they're just going to be brand new, state of the art. The whole foundation's changed. That's not necessarily the truth either. These are hybrid systems, right? We have our standard computer systems, our standard compute, silicon-based chip systems that sit on top of these systems and are being used to interface with them. So, our next gen computers are going to be, hybrids, right? They're going to be utilizing this extra capability, but the architecture to do that is where it gets really interesting, right? Because not only do you have the hardware, you also have the software, right? And what we're seeing out there right now are companies like Amazon and Microsoft and IBM. They're building out these cloud services for providing developers and scientists with these access to these these quantum environments, and they're giving them whole development platforms to actually perform their experiments and their processing. So it's already started, right? The challenge here is that where we're at today, we're not going to be doing the equivalent of what the frontier can do today, right? It can only do so much, right? And I'll go back to this problem that we have, and that problem is with errors, right? When you're in the quantum realm, right, you're talking about subatomic particles and such. You can have temperature, you can have microwave, you can have cosmic rays, you can have a lot of noise that can interfere with these systems, right? And that causes errors, right? And so you have to basically push these through these processes through a number of different error correction algorithms in order to come up with a clean result. Which, when you think about it, that's one of the biggest challenges out there, right? That's why when we look at the different types, right, like that photonic version, it's a lot slower in its ability to manipulate and come up with answers, but it's a lot more stable, right, compared to like the super cool superconductor approach. So this is where, when we look at the different technologies that are being used to build these machines, there's going to be eventually one that wins out. It's going to be the one that gives you the most bang for the buck, from an accuracy point of view, less errors, and it's able to compute and reliably at the same capability as our current electronic based solid state CPUs, right? So,
yeah, in every industry, there's always a sort of a technology or an implementation of a technology that takes over and becomes standard. If you want to go back in time again, back in the days of beta and VHS, eventually VHS became the standard in one. We had everything back in the day from those, tape-based mediums. We had, if you remember, laser discs.
Laserdisc. I remember
which
them.
essentially, like, a laserdisc was what? It was basically the size of a vinyl record.
Yeah, it was
that
cool.
Played movies. They were pretty cool, but
Big
they weren't
CDs.
overly practical, right?
Yeah.
And then eventually we moved on to obviously like DVDs and Blu-rays. I still have a huge collection of those here. And now, of course, everything's just streaming, right? So everything goes through sort of an evolution, but eventually, as a society, we decide, okay, this is the best way to deliver this, and I guess that's what you're kind of talking about. But how will this quantum computing disrupt or advance certain industries? There seems to be a lot of different ways that it's going to be poised to revolutionize things, and like we talked about earlier, I think this combination of AI and quantum computing is a real I guess you would call it a advanced combination that's going to propel us into the future in many different areas. We can look at, drug discovery and development, basically because we can simulate, molecular interactions and predicting drug efficacy, and that type of thing more accurately. We could develop new things faster, and end certain diseases that have puzzled us forever, like cancer or Alzheimer's. Certainly, financial modeling is another area where we can create better simulators and to understand how the economy works and how to improve it, which is still something, interestingly enough, the economy is man-made, but yet oftentimes we can't get a handle on. I mean, we've been trying to fix this inflation and other elements of the economy since COVID, which is always amuses me that it's something that's man-made, and yet we're trying to figure out how to fix it. It's almost as if the economy is like an organism, right?
Yeah.
Obviously we talked about cybersecurity earlier. I think, making things more secure, but, in the hands of bad actors, this quantum computing combined with AI could really open up, holes in a lot of our more traditional systems.
And the other thing too is, like, we talk about breaking current security. You can imagine if HTTPS is broken tomorrow, if all our SSL and TLS and all those protocols are all just suddenly broken, right? You can imagine the havoc, right? So luckily
Maybe
we're not
Y2K all over again.
Yeah, we're not there yet, thank goodness. Yeah.
I don't know if you remember that as vividly as I do.
I do.
There was quite the fuss over for those of us that were maybe too young at that point or not born yet. That was what was it? It was all the computers weren't built with the idea of going past the year 2000 in mind, which seems like insanely short-sighted when you think about it, right?
Yeah.
That really we started to have computers emerge in sort of the 80s in some rudimentary way, and then through the 90s, and I mean, like, they really hadn't planned past the year 2000, and the idea was all these systems were going to be set back to zero and implode or whatever all the theories were. And I still remember New Year's Eve, the year 2000, that everybody was kind of on the edge of their seats because people were like, are the airlines going to stop working? At that point, we started to depend on computers for quite a lot. I mean, not as much as today, but quite a lot. And there was this sort of impending doom of Y2K. And then you layer on top of that the idea that these different religious factions were saying the whole world was going to end in the year 2000. And it was quite an interesting New Year's Eve. I'd like to see the statistics on how much alcohol was drank on that New Year's Eve.
Yeah. I remember that too. I mean, I was manager for many different systems at a particular corporation, responsible for those. And a lot of people don't realize that the systems that were built, or in use, were actually, very buggy, and they had, and this wasn't a hoax. This whole Y2K thing. There was a lot of work that was done before midnight to fix the problem, and it turned out to be, well, it wasn't that bad because in reality it was fixable, right? And it and it was addressable, and anything that was important was fixed, right? And it was monitored, and if something broke, they fixed it, right? So everybody can look at that and say, "Oh, it was a non-event. It was a bunch of, it was a bunch of hocus pocus." But no, it was a lot of work. That's what it was. There's a lot of burden cost that the companies had to take on to fix their systems. That get it done now, get it done dirty, just get it done, right? And if you take that attitude, stripping off a few, extra characters on the ear and such, that, because of the cost of memory, that all made sense at the time, right? So it was real, but we think about it now, it's laughable, right? Why would somebody do that?
Well, like I said, pretty short-sighted, but we've been known to do some short-sighted things over time. Yeah.
Yeah.
I think, Yeah, I mean, a few other areas that we're going to see some advancements. So you touched on the idea how complex weather systems are. So again, climate modeling and weather forecasting, I think is a huge thing. If you look at what's about to hit Florida,
I
which is
know.
supposedly one of the biggest hurricanes in history, essentially. And oftentimes, we don't predict these things with enough time for people to sort of get out of the way, and people become so complacent that they just don't want to leave. And even this time, we hear them saying, "Hey, like this is different. You need to get out." But evacuating that many people is not a simple thing. Back in the day of I think it was Katrina or one of those hurricanes, there was a lot of logistical problems with getting people out of areas in a short amount of time. In fact, years ago we had huge, well, I mean, we still have them, but we had a lot of really devastating wildfires. This is sort of related, but um, we had in Fort McMurray, where my brother lived at the time, they had seen fires just outside the city and didn't think much of it. And all of a sudden, it just really took over. And to the point where people were trying to get out and the roads were blocked. People had to abandon their cars and find other ways to sort of escape the flames because it just created this clogging of roadways and things. So it's, the more we can predict these things, the better, the population is for sure.
Yeah, we're seeing many, many different types of weather events across the globe. And yeah, and even think about, well, could it be utilized? Could model systems be utilized to help predict, forest fires or forest fire behavior and that kind of thing as well? Not just storms, but catastrophic events. How would they behave? So yeah, lots of capabilities there for sure, and you know, building these models on kind of the AI, platform, and the AI platform is built on top of this quantum, super uh, super processing platform, and all these different layers are coming up with some, call them helpful answers for
Well, it's
mankind.
that combination, right? So, like we touched on it a bit earlier, but maybe we should get a little bit more into it. So, this idea of providing quantum computing power to these AI systems is really going to supercharge it, right? It's almost like giving Thor's hammer to Superman, right?
Yeah. I've never really looked at it quite that way, but yeah, yeah, yeah. We think about can you enhance on top of enhancing, right? Can you supercharge what's supercharged already? And that's what we're really talking about. So you know,
hmm
it's given it the gas, so to speak, and the challenges that we have today are we haven't quite figured it all out yet. But once we do, right, that's the
hmm
huge potential here, right? And that's why you see a lot of companies. There's a lot of investors are dropping millions and billions of dollars, not just in AI, but in quantum technology as well, um, because they see that, right? They see the potential, right? In being able to work forward and all these benefits, all these different areas, it could be worth so much, right? And with that in mind, um, we just can't necessarily fathom what's going to happen in the next 5 years, right? But if you think about the challenges that we have to overcome, first, this idea of error correction is one. How we can scale up this technology right now, it's not really, doesn't scale up very easily. Like there's only like I said, a couple hundred qubits involved right now. The technologies don't scale up to 20 million very easily. So it doesn't do that. There's
hmm
limitations on what we can do from a point of view of hardware and what we can build. And the idea is, if you're dealing with something so small, it's this very extreme environment. Um, Realistically, can we actually build anything that's consumer based? Even probably not, right? It's always going to be these monster machines in the background for now until someone has isolated this a more stable approach, right? Um, and there's also something called quantum decoherence. So we want a qubit to maintain its memory, so to speak, and retain its state. When we look at it and observe it, we want it to maintain that state for a certain amount of time instead of kind of breaking down. It's like trying to keep a soap bubble intact, right? Um, yeah, so it won't pop. The methods that we're using are not necessarily the end result, right, of what we're looking for. So that's one of the big challenges that are slowing us down. So a lot of the the correspondence we've been reading, and that's the research that we've been done. They call this the noisy intermediate scale quantum era, and
That's a mouthful.
yeah, so it's noisy. It's using exotic equipment, and it's not able to necessarily be totally useful. And we need a lot of very involved equipment and people and knowledge in order to run this, right?
Will there be like a reciprocal effect of AI helping us figure out some of these
Yeah,
limitations in quantum computing, right? And that,
yeah,
or then that would make that technology better, which would make AI better, and then everything would kind of snowball from there. I mean, everything may be early now, but I mean, when you think about it, we're all walking around today with what would have been considered a supercomputer, back in the day, right? They took a spaceship to the moon with less power than we had in calculators, in Texas
yeah,
Instrument calculators in the 80s. And now you look at what's in our pocket in terms of, smartphones and technology. Again, it would be considered a supercomputer. So it's not outside the realm of possibility that we could see this very quickly accelerate, in the next five
yeah.
years, for example.
Well, this is the same. I mean, if you look at it from a point of view of AI, right, the arguments and then the reasons for investment and all that's all very much in line, right? Same payback models and so on and applications. It's all very much the same, right? What you know, if you look at what OpenAI is talking about and a lot of their scientists they're talking about this nonlinear progression, right? This exponential growth and capability, and then on top of that, you use AI to introduce better working models for quantum computers, and then from there, you evolve the quantum computer even further. It's one step after another step after another step, and you are doing this curve that goes steeper and steeper and steeper, right? It's incredibly fast, right? And this is where there's fear, I think, too. The other side of it.
Yeah, that could spiral like out of control. I mean, what
Yeah,
you're describing is this idea of the of escape velocity.
yeah,
So the idea of escape velocity is when something gets so much momentum that it's able to break free from its like gravitational pull, right? In other words, like there's sort of a reasonable expectation of growth and acceleration of just about anything, technology included, and this combination of quantum computing and AI, we could reach that escape velocity much faster than maybe we want to,
yeah.
we're gonna
So
we're gonna end
we've
up
just spiraled back to season one in our super
yeah
intelligence conversation.
brought
Way
it
to go,
back
Jason.
to we just made a quantum leap back to season one.
That's right. That's right.
Sorry, I couldn't resist the pun.
That's great. Yeah, and the other thing too is that with the capabilities. I mean, you can almost see like whoever gets this right, these technologies, and starts to bend that curve up even further. I mean, this could cause geopolitical disruption. This could cause um, you know severe economic issues, and there's a lot of potential. It's not always good with this, right? So all my fingers are crossed, of course, but the potential here is can be kind of scary, right? And you think about these systems right now; they're kind of at their very beginnings, right? We don't really have a clear winner for the technologies to utilize. Um, the systems really don't scale at a commercial level. We don't have the even close equivalents of the computing power that we have today in our standard technology. And the QPU, we'll call it the QPU. That's hard to say. Can you say it backwards? Anyway, so the idea of managing all the inherent problems with quantum computers, like error correcting and coherence and that kind of thing. But how close are we? Right? I mean, a lot of people basically said 5 years ago, we won't see a quantum computer in another 25 years, right? 5 years later, we have commercially accessible, very low scale quantum computer systems, right?
Mm-hmm.
Not a lot of them, but they're out there, right? So we also have AI, right? Same kind of thing, right? It's growing. So what's really going to happen? Are we 20 years out before we have an equivalent? I mean, if you look at if you do some research and you do some sampling out there, that's the current guess, right? I don't think we're going to 20 years out. I think with AI, right, with our learnings of technology, with our need to drive and solve, our power challenges and our climate challenges, I think there's going to be more and more invested in this in order to attain the golden fleece, Jason. And I think we're like a decade away. I think they're that close.
If you look at, the advancements over the last, even 5 years, 10 years to, the things that we're seeing now with the advent of, lots of different technologies, right? Autonomous vehicles and augmented reality. And now, like we talked about today, quantum computing and AI. It's easy to say that, we'll never achieve this or we'll never get there. The thing is, we just don't know. There's a quote: "If we knew the unknown wouldn't be unknown." Now, will it?
I don't know.
Thank you for listening to the Probability Podcast. Please join us next time for more